How many times have you seen someone put two images side by side or flip back and forth between them and then ask you which one's better? Maybe they're comparing cameras, filters, or a new processing technique, and usually that's where it stops. This one looks better than that one. But the problem is those comparisons don't really tell you what's actually changed in the image. Hi everyone, I'm Brent. I'm a scientist, programmer, and astrophotographer, and I like digging into what's really going on under the hood so you can make better decisions and get better results. Every image is just an XY grid of numbers, and one powerful way to understand those numbers is by taking a cross-section, literally drawing a line across the image and looking at how the intensity changes along that line. When you do that, you're not just saying this looks better, you're actually seeing how different methods affect the data. That's especially useful in astronomy, where you might want to compare two images and ask things like, what did this filter really change? What did this stretch do differently? Where is detail being gained or lost?
Before we go any further, there's an important distinction we need to clear up, and that's the difference between raw data and what we eventually see in an image. When a camera captures light, the data it records is linear. Each pixel value is directly proportional to how many photons hit the sensor. In that raw state, the numbers actually mean something. If one pixel has twice the value of another, it really did receive twice the signal. But the moment we turn that data into a real image, things change. Now we're making choices. Here, for example, I'm using the histogram transformation tool in PixInsight. This tool is one way that we map low to high signal to black to white pixels, and we have a lot of choices in how we can do that. We can control the white point in terms of what gets defined as white in the image, and we can control the black point, which defines what section of data is going to be rendered as black pixels. And we can also control everything in between and how that's mapped from black to white. And in almost all cases for astrophotography, that mapping is nonlinear. We use stretches, curves, and other transformations to squeeze a massive dynamic range into something our eyes and our monitors can actually handle. And that's where image comparisons get really tricky, because I could take that same data and stretch it a different way and end up with somewhat of a similar image. And this is where image comparisons get tricky. So many things have happened, it's hard to tell what differences are related to image visualization and what is attributable to the thing being compared. Two images can come from very different underlying data, but if they're stretched differently or adaptive algorithms compensate for those differences, they can end up looking surprisingly similar. Here I have two narrowband images, one using a 6nm bandwidth filter and another using a 12nm bandwidth filter. The question is, how do these compare? So I'll use a new adaptive stretch tool to let us see the details we're interested in. I have the settings dialed in. I'll apply it to the 6nm image. Do its processing. We get a result. And I do the same thing with the same settings to a 12nm image. And, well, it's kind of hard to compare. That's why it's often so hard, especially when we're looking at heavily stretched images, to tell how a camera, a filter, or a processing step affected the data. What you're seeing isn't the data itself, it's a visualization of the data, the transformation of numbers from a sensor to a black versus a white pixel in an image, shaped by the black points, white points, and all of those nonlinear mappings. This is exactly why tools like image cross-sections are so powerful. They let us step back out of the rendered image and look directly at how the underlying signal behaves, before our visual system and all of these stretching choices get involved. So let's jump over to our cross-section tool. So here I'm in Astro Cross-Sections. I'm going to load image 1, and we're going to start out with that stretched image that we just did. So I'm going to load up the 6nm stretched image as image 1, and I'm going to load up the 12nm filter stretched image. I'm going to do the half resolution as image 2. Now, by default, an auto stretch is turned on. This auto stretch is not applied to the data we're going to look at, just to the images up here to help you do the cross section. These have already been stretched, so I'm going to turn that off, and this now looks like the previous image. So to do a cross section, you just click in a location and drag your mouse out to select a line, and you can now see this cross section. Image 1 is our 6nm, and 12 is image 2 in orange. So to look at these two, they look really similar, especially as we go down this slope and look at the stars. So there's some slight differences down in the depth of the head here, but it doesn't look like there's that much of a difference between the 6 and 12 nanometer filter. This is where the images can get really confusing. Let's go back and look at the raw data to see what's actually going on. I'm going to click on the clear images to clear out our images and now load the original 6 nanometer data and the original 12 nanometer filter data. These start out in a linear state. I'm now going to turn back on the auto stretch since they're in a linear state. And again, this only influences how they show up here, so we can select the cross section. It will not influence the intensity we see down here. So now I'm going to do a cross section. And now there's substantial differences in the data. We've not applied that black point and white point and stretching in between. We can see that the 6 nanometer filter and the blue line here has eliminated so much more noise out of the sky pollution that we have a lot lower signal compared to the 12 nanometer filter. So that influences multiple things about the data so that we can actually understand and compare what these filters are doing. This is very different signal and noise levels that we are capturing in the images. And we can only see that through this type of cross-sectional analysis. To look at the images, you won't see those differences. As an extra option, if we have a really big dynamic range here, we can also turn on a log scale and be able to look at very small to large values. This will become important when you look at things like stars that are tremendously more bright compared to the background. So if we were to uncheck the log scale, we can see that that would just go to essentially zeros. The log scale lets us look both at the high intensity and the very low intensities at the same time. In using this tool, you may find that you want to zoom in and be a little bit more careful with where you're exactly doing your cross section. So if you put your mouse over either image and use your scroll button, you can scroll in and it will zoom into the image. It takes a little while to respond, especially if you're using a large image. If you want to pan around, you right click and hold, and you can pan, and you'll see that both of the images are synchronized across the two. So now you can have a little bit more precision about exactly where you're pulling the line from. We can zoom in some more there. If you zoomed in and totally unhappy, and you're unhappy with how you've selected the image region, you can then go down and set reset view, which will take you back out. Once you have a cross section, it can be really useful to just look at it in a graph, but if you want to do other analysis that's more advanced than this particular app can provide, you can click on the bottom button down here to export a CSV. It'll pop up a file dialog, so you can give it a name, and it will save it as a CSV file that records the intensity as a function of the pixels that you selected. So if we were to go look at that, we would see that we get that distance in pixels, the image 1 intensities, and the image 2 intensity if you wanted to go in and do any other type of plotting or analysis on those lines. One of the assumptions of the Astro Cross-Sections app is that your images are already registered when you've done things like stacking. It's recognized that not all images will be exactly aligned correctly, so to demonstrate what can happen here, I've cropped a version of the 6 nanometer filter, so it's a subset, it's a different size and a slightly different alignment compared to the original image. If I were to now open up the 12 nanometer full-size image, it's going to search through, do its best job to do an initial alignment, and the software recognizes that there is some registration issues detected. If you look down here in the bottom, you'll see that there is a shift of more than 162 pixels in X and 65 in Y. And if you were to try to do a cross-section, we could see, ooh, these do not line up correctly. If you run into this, you can use the Register Images button. It won't always work perfectly, but in this case, it should do a good job of aligning the images, getting them registered, and will report back that there is less than a pixel error. We can now see that those cross sections are setting up correctly. So If you need to use it, I think using other registration tools and software like Cyril or PixInsight are going to be far superior, but this will get you through. So far, everything that we've seen has been for mono camera images, so you only have one grayscale channel. We can also handle color images. So I'm going to clear out the images. I'm going to load one, and let's look at one of the original color images that I've worked up. So this one's already been stretched. And when you load a color image, it'll ask if you want to convert it to grayscale or luminance, or if you want to keep it as RGB channels. We've already seen the mono, so I'm going to say no, keep the RGB channels. And you'll see that our graph has now been split into red, green, and blue contributions. I'll go load image 2, load a second RGB image that's the same size and of the same object. Now, this looks a little bit funny. That's because our auto stretch was still on. So if I turn off the auto stretch, now our images look correct. And now we can go do a cross section and compare what we see across the images. So looking now kind of across what was happening for this yellow region, we can start to see the difference in this more muted versus the more vibrant can start to show up in differences in the red, a little bit in the green, and we can also see that based on where we started near the core here, there was apparently some differences that were showing up in the initial parts of the image. So this will enable you to do R, G, and B analysis, and when you also go to use that export CSV, you'll get each of these channels so that you can go back and do an independent analysis for each of the color channels. So by this point, I hope that you're saying, this is great, how do I get a copy? Well, all of this is hosted on GitHub. I'll provide the link down in the description with the URL that you see here. If you have Python and know how to run Python, you can download the repository and run the app astrocross.py. If you don't have Python and just want the executable, scroll down until you see the executable with a link to the .exe. You'd use right-click, save link as, and you can download it to your local downloads folder and simply run the executable from there. It should just run up and start working like I've been demonstrating here. Since recording the video, I've made a few improvements to the software. First off, you may notice that the fonts are a little bit bigger and easier to read, and there's a few extra buttons and options. I now display the data type, whether it's a 32-bit float that you might see from your raw data, or it may indicate that it's an 8 or 16-bit int, so that it gives you a little bit of a feeling as to what data you're really working with. One of the features that I've also added is that now the legend includes the file name, so it's really clear which file and image is associated with which line in the graph. I've also added the option for converting this to a histogram so you can compare the statistical distribution of the two images. So in this case, this is looking at the intensity or how many pixels are at a given intensity. And we can see here I've labeled out the median values and illustrated them here as vertical lines. So we can see that the median of the 12 nanometer is at a much higher intensity compared to the 6 nanometer. And this can help give you a good or better statistical understanding of the differences between the images in addition to what you get out of a cross-section. This also works with the log scale plot, so you can turn that on or off so that it's on a log scale for the y-axis. If you export the CSV, it'll also export the histogram when you're in histogram mode, or cross-section when you're not in histogram mode.
All right, let's recap. What I really want you to take away from this is that images are a visualization of the data. By the time you're looking at something on your screen, black points, white points, stretches, curves, and adaptive algorithms have shaped what you're seeing. Two images can look very similar, even when the underlying signal may be different. When you look at the data directly through cross-sections, you're no longer guessing. You're not asking which looks better. You're asking what actually changed. In the end, we do care about how the final image looks, but when you're comparing filters, cameras, or settings, the linear data may provide the real answers that get masked based on how images are visualized. And that's really the goal of Astro Cross-Sections. It's about giving you a way to build intuition for what your camera, your filters, and your processing choices are really doing to the data. If you're someone who likes understanding things at a deeper level, whether you're into astrophotography or image analysis, please subscribe and join me to get more content like this. If you try out this program, I'd love to hear how you're using it, what questions it helps you answer, or what features you'd like to see next. Maybe build it as a PixInsight or serial script. Well, all the links are in the description. Thanks for watching, and stay curious.